Hello and welcome to the second of 6 films about the kinetic theory. This one deals with changes of state. The first one dealt with states of matter. So this one is actually dealing with what's happening to the particles as we go from one state to another. Okay, we are studying kinetic theory here, so try and get into the habit of mentioning particles when you actually talk about these things. Okay, we're going to study heating and cooling curves and think about what's happening to the energy of particles when substances are changing state. And we're going to think about how the melting and boiling points of substances can change as they become impure. Okay, so let's have a look. Here is something called a heating curve. You could call it a cooling curve, but it looks more like a heating curve because we're adding heat. Okay, so we are going from a cold temperature to a warm temperature. A cooling curve would just be this in reverse. Okay, but I want to consider the different kinds of energy changes that we've got going on here. Now remember that the temperature of a substance is related to the kinetic energy of its particles. Okay, so if ever the temperature is changing, the kinetic energy has to be changing. Okay, I'm probably going to say quite a lot of things about this graph. I'm not going to have room to write them all down next to it. Okay, so here we are, right? We are at section A, we are in the solid state and we are adding heat. So this, perhaps we've just put a beaker with an ice cube in it on top of a Bunsen burner. And we're not changing the rate that we're adding heat at, so it's just constant supply of heat. So in other words, the energy should be rising at a constant rate. But look, it's not. Okay, it rises at a constant rate and then levels off, and then rises at a constant rate and then levels off again. Now, when you're looking at a heating and cooling curve, you should recognize these flat areas as places where the state of the substance is changing. Okay, so from this point up to this point, we haven't stopped adding heat, but the temperature has stopped rising. That means the kinetic energy must have stopped rising, but we're still providing energy, so the substance must still be absorbing energy. What's happening? Well, the potential energy of the substance is rising here. Okay, so at these flat stages, the potential energy is rising. Why is it rising? Well, because the particles are getting further apart from one another. If we're going from solid to liquid, as it says here, right, so this area B of the graph is where we're turning from solid to liquid. In other words, we're melting. Okay, the potential energy is rising because the particles are moving further apart. They have the potential to stick back together. Okay, so they have the potential to do work. They're not starting to move faster. Okay, we made them move faster by heating them up and raising their temperature. We're now keeping the kinetic energy the same, but the potential energy is rising because their positions relative to one another are changing, and the forces that interact, that exist between the particles come into play. Okay, notice that until all the solid has turned to liquid, the temperature won't rise. Okay, bear in mind this is for a pure substance. Okay, right, we get to here and now the temperature starts to rise again. That means that the kinetic energy is on the way up. Okay, kinetic energy is rising. The potential energy isn't, because we're staying in one state. We're staying in the liquid state, so the particles are just about the same distance from one another as they were before, but they're starting to move faster and faster and faster, so their temperature is going up. Then we reach what is called the boiling point. Okay, so here is the boiling point. That is a temperature that we've reached. And notice again, the temperature stops rising. That's because the particles are now moving fast enough to evaporate at quite a fast rate, okay? But their temperature stops rising. So all this time that the liquid is boiling or turning into a gas, the temperature is constant. That means the kinetic energy is constant. So it must be the potential energy that is on the rise again, okay? Why is the potential energy on the rise? Because we are now separating particles from one another. They have the potential to stick back together because of these forces of attraction, okay? And then finally, once all the liquid has boiled, we get to the gaseous state and we start warming the gas up. We're still providing energy at the same rate, but now, again, it is the kinetic energy that is increasing while the potential energy stays the same. Okay, we've got phase changes here marked on the graph. As the solid turns into a liquid, it melts. As the liquid turns into a solid, it freezes. These are everyday terms that we all should know the meaning of. Okay, then the liquid is increasing in temperature, and as it starts to boil, so this is the boiling point, mark that there, that's the boiling point, and here's the melting point. All right, we are starting to vaporize or evaporate the liquid and condense the liquid in the return direction. So imagine if we were cooling this substance, we'd be removing kinetic energy, then the kinetic energy would stop changing, we'd start removing potential energy as the particles came closer together, then the kinetic energy would fall once all the liquid had condensed back to a solid where the potential energy would start to fall again, and once all this liquid had solidified, only then would the temperature start to fall again. So some important points to note on this graph. Lots of stuff I've talked about there. Temperature remains constant at the boiling point, and melting point of a pure substance is probably one of the most important things about that graph. Okay, here are a couple of heating curves and cooling curves. So this is actually a cooling curve. This thing's cooling down, whereas this thing's heating up. Okay, but they're showing what is happening to the boiling point and to the melting point of a liquid as it cools or heats, depending on whether there are impurities present. Now notice, look carefully here, there's two lines on this graph. There's the blue line, and that shows a pure liquid, okay, pure liquid that freezes at a certain temperature, and the temperature doesn't change, okay, until it's all frozen, and then it starts to cool down again. Here's the red line with the impurity added, and notice the melting point is lower, okay, or the freezing point is lower. This is why we add salt to ice. Why we add salt to water on the roads where I come from. You don't really have that issue here in Perth, but this is why we add salt to the roads, because it makes the water freeze at a lower temperature. But notice also that there's a range of temperatures over which the liquid is freezing. So key points to note from this graph is that the melting point is lowered and it's not so sharp. Okay, it's melting or freezing at a range of temperatures rather than a precise temperature that it did before. Here's a heating curve. Okay, here's where the liquid starts to boil, notice. Okay, so this is actually 100 degrees, so we're probably dealing with water here. Okay, so here's our boiling point. Notice there is the blue line. Okay, there's our blue line, reaches the boiling point, temperature stops rising. Okay, but if we've got an impurity, so this is our red line, notice that that temperature stops rising at a higher temperature. So the boiling point is higher when you've got an impurity. All right, and we'll look at that again later when we come to vapor pressures. And what we can't see so well on this graph is that it's not as sharp. Okay, so the difference that we get when we add impurities is that the melting points drop, the boiling points rise, and they stop being such precise temperatures. Okay, now as I've said a couple of times, there's a lot of important points covered in that film, and I didn't have space to write them all on the slides. All right, make sure that you've got those important points in your notes. If necessary, go back and add a few. All right, there should be quite a few key points coming out of that film. And once you're ready to move on, go on to the one about gas behavior. That's the third film.